So welcome everyone in the second talk of Sukanta Das. So today we will talk about iteration of rational functions. Over to you, Sukanta.
Okay, thank you. So let me share my screen. Yeah. So today's talk will be basically on the rational functions, in particular polynomials, and we'll see how the iteration of polynomials basically depend on the critical value, or I can say critical point uh, of the polynomial. And after this, we will just see some useful and important properties of Julia set of the polynomial as well as for rational functions. And then we'll move on to the classification of Fatou components. And if time permits, then we will like illustrate these things by showing some examples. Okay, so maybe I should mention here, I should have done this in the first talk, that the books I'm referring here is, so basically my talks will be basically uh, like coming from these two books. So first one is iteration of rational functions. This is by Alan F. Dearden, and the second one is that dynamics in one complex variable. This is by John Miller. So basically, I'll be trying to covering like these two books. Yeah. So let me start. And here, let me define what is the degree of a rational map. So say R is my rational map. It is from C hat to C hat. Then the degree of R. So obviously we know that rational map is of this form, say Pz by Qz, where Pz and Qz are polynomials with no common factors, and the degree of R is defined by the maximum of the degree of P and degree of Q. So this is basically stands as an instant. Like one can just see this, like if you take any point from the code, like from the codomain, which is C hat, if you take any point from C hat, say Z naught, and you take the inverse image under R of this point Z naught, then you will have exactly m many pre-images, counting multiplicity. So this m is nothing but the degree of the map R. So, okay, now I'll say some facts. So this is an useful fact that a rational map, say R, satisfies Lipschitz, okay, Lipschitz condition means, so here, as I have told earlier, that here we are talking about the spherical matrix. So corresponding to this metric D, so if you take any points
Yeah.
let's
Sorry
say Z
for
and W.
yeah. I have
Yeah,
one small question. So you define
yeah,
R equal to P by Q. So like P and
yeah.
Q may be co-prime. Otherwise, we can take Z by Z. Right?
Yes, yes, yes.
Means-
Yeah,
So here P and
yeah.
Q are
That thing I
co-prime.
have,
Yeah.
yes,
Oh,
I have said earlier that
oh
they have
okay,
no
okay.
common
I see.
factor. Yeah, yeah.
Okay,
Thanks,
fine.
thanks. Okay. So now, so this means that you will always have some constant, positive constant m, by which you can uh, have this inequality. This holds for all z and w in C hat. So where for some m greater than 0. So this actually holds for any rational function from C hat to C hat. So this is a fact, and I think it is not difficult to check. So just keeping this in mind, we will progress further. Okay, now
Sorry,
let me,
what is D? D is which metric?
yeah, D is a spherical metric.
Ah, spherical. Okay, okay.
Yeah, thanks. Okay, now this is an important theorem, or you can say important property for related to the Fatou and Julia set. So let me state it here. So for any rational map R, and any, if you take any natural number n, then the Fatou set of R is same as the Fatou set of R, okay, Rp. And similarly, the Julia set of R is same as the Julia set of Rp. So this is a nice and it is not a difficult thing. So maybe the proof can be done in a easier way. So just let me just give the idea. So here, because I have just taken this fact that every rational map satisfies Lipschitz condition, so I will use this fact here. Okay, so take say S to be my new map, which is basically Rp, where P is a natural number. Now, if you just consider Sn, Sn means S1, S2, S3, S4, like the composition of S n times, and your n is going to infinity. So if you take this family, so this is a family of rational functions, but this is a subfamily of this family Rn for any n greater equals to 0, right? So this is a subfamily, and if we see that if my so the first thing is that first of all I will assume that the Fatou set of R is given to me, and then I'll show that this is same as the Fatou set of Rp. So that means here I am getting that the Fatou set of R is subset of Fatou set of S. Means if my Rn is a family of functions which is equicontinuous in a domain D, so that in that domain my function is basically forming a normal family, means that becomes a Fatou set. So since Sn is a subfamily of Rn, so Sn will be always yeah. So that means whenever I have a domain of normality for the rational function R that belongs to the Fatou set, so that will always belongs to the Fatou set of S, since my Sn is a subfamily of Rn, right? Okay, now, okay, let me keep it here so that you can all see. Now take any, say k from natural number union 0, then consider Rk. So Rk is a new rational function. So Rk will satisfy Lipschitz condition. So that means there exists some m greater than 0 such that d of now you consider this family RKSN. You can put Z here, RKSNW. So this will be by Lipschitz property or Lipschitz condition. So that is D of SNZ, SNW for all ZW in C hat. Since my RK is satisfying the Lipschitz condition, so I can write this. Now, this immediately gives me that my RK SN such that, or simply I can write in greater equals to 0, is equicontinuous whenever whenever Sn is equicontinuous by the above inequality. Okay, so that means I'm getting that the Fatou set of S is a subset of the Fatou set of RKS, and this K is coming from this set of natural number union 0. So that means if you take the union, so take my K to be 0, 1, 2, up to P minus 1. So it is enough to take the values of K from 0 to P minus 1 and take the union of these RK Sn such that n greater equals to 0 for these values of K. So if you take the union, so that means if I write like union K equals to 0 to P minus 1, RKSN such that n greater equals to 0. So this is nothing but Rn such that n greater equals to 0. So that means I'm getting the initially I got this, and this holds for all K. So if I take the union of those K which are in 0 to P minus 1, so then I am having that my f of S, this f of S is a subset of the Fatou set of R. So that means I'm getting the Fatou set of S is a subset of the Fatou set of R. Since I have taken the union, so this family is due to the rational function R itself. So my Fs becomes a subset of the Fatou set of R. Okay, so that means initially I saw that this is 1 and this is 2. So immediately this follows that the equality. Therefore, the Fatou set of S equals to the Fatou set of R. So similarly, we can do for the Julia set also. So I'm skipping this. But the thing is that here is an important note.
Okay, here is one point maybe. The equality union K from 0 to P minus 1 RKS power n is equal to maybe R power n greater than equal to P.
No.
Because S is R power P, right?
S is R power P, yeah, correct.
Right. So, yeah, S is R power P. So if you take n equal to 0, you can't find R power P minus 1 in the left hand side, right?
No, you just simply calculate. Let me do it. If
Okay.
you just simply check the union of what is the value of
Say
this supposed. So,
yeah.
Okay, so first of all, I have say RKSN. So this is the basically this is my function where my K is from 0, 1, 2, P minus 1, and my N is from 1, 2, 3, up to infinity. Now
S
you
is
put
R
your
power P.
S is R power P. Okay, no issue.
Yeah.
So that means this will be RK S, not S. I write it in terms of this will be PN. Yeah. So now you put, first of all, you put your K to be 0.
And N maybe 1.
If you put K to be 0, you are having yes. So by choosing K and N according to your choice, you can cover that. You can see that all the elements of this. family is covered.
You can, right? No, but you can cover up to means r power starting from r power p, because r power p minus 1 you may not cover, but that the initial point may not be matter. Means the proof is right, but I think r and up to r power p minus 1 may not cover. As you can see,
No, no,
k
no,
is
no,
0. Okay,
no, no.
so if you, mhm.
Everything will be covered. Everything will be covered. So
Yeah,
just you have
yeah.
to
So
take
okay,
care of this thing only.
but how can we get r power p minus 1 set? So if we can take k lowest is 0
No,
and
if you here if you
mhm,
put in here if you put
mhm.
okay, so okay. So here maybe I should write in, yeah. So I have, see here I have written n equals to 0 from n is going from 0 to infinity. So here 0 is also here. So if you put
Okay.
n to be 0, got it?
Oh, I see.
If you
Okay,
put
there
n
is
to
a
be
0
0,
also. Okay.
yeah. Nice.
Okay, okay. Then it
Okay,
will get. Thank
okay,
you.
okay. Fine. Okay, now let me give an useful note here. Okay. So the idea by which we have proved this is basically coming from this Lipschitz condition. And this holds for all rational functions, but unfortunately, this doesn't hold true for any transcendental entire function. So that is why we cannot use this method of proof for the transcendental case, although this result holds for transcendental setup also. But the proof will be slightly different, and the proof, let me write, the proof will depend on two facts. So for the transcendental interfunction, the proof basically depends on two facts. The first one is the fundamental normality test, which I have mentioned in the first talk. And the second one is that this is like a simple idea that if you take any transcendental interfunction, say f, then fn for n greater equal to 2, this fn will always have, or simply I can write always have, this always has infinitely many infinitely many fixed points. So it is always known to us that a transcendental interfunction, it has either no fixed point or it has infinitely many fixed points. So even if my f does not have any single fixed point, but if you just take the second iterate of it, it will have infinitely many fixed points. So these two idea will be required for the proof of this. So maybe I'll skip this because I am in a way to like cover more of this. So yeah, so I'm just telling that what this setup will not be or it will not hold for transcendental case. Okay, now one more thing is that last day I mentioned that completely invariant set. So I maybe recall what is completely invariant set. Suppose you have a domain U. So if f of u subset of u and f inverse u subset of u, so this case it is called forward invariant. This is called backward invariant. So if these two hold together, then I will say that U is completely invariant set under F. So the thing is that here for rational maps and even for transcendental maps also, the Fatou set of R and Fatou set of and Julia set, okay, and the Julia set of R, these two sets are completely invariant. So maybe it is a good exercise for you to check just by one condition, which is by the definition of equicontinuity. That is the only simple case by which you can just simply check it. Continuity. This is not a difficult thing. So one can take it as an exercise. It's very easy. Okay. So yeah, so Fatou set and Julia set for rational maps as well as for transcendental maps, it is completely invariant. These two maps, these two sets are always completely invariant. Yeah. So now, okay, now maybe I should define some new thing which is called periodic points. So the dynamics of a uh, function, rational or transcendental, it actually depends on few interesting points on the complex plane. So these periodic points are one of those important points by which we can calculate or check the dynamics of the function. But yes, it is not the only way to check. There are some difficulties in it. So I'll first tell what it is. So suppose we are starting with a point Z0 and keep iterating this point. So this is Z1 second image, this is third image Z2. So this is Z3. And maybe say after fourth iteration, so this is F, and F, this Z3 comes back to the point Z0. So that means my Z0 point is periodic. But here I just take care that which is the least natural number for which this condition holds. This condition holds that f p z naught is equals to z naught. P is the smallest natural number. So I'll take the smallest natural number for which this holds. Then I'll say my z naught is a periodic point. So in particular, if I take p to be 1, so z naught becomes a fixed point. So now there are few things. The first one is which is a multiplier. So what is a multiplier? So multiplier is that multiplier of a periodic point. Okay, so here I will say that this z naught is a periodic point. Okay, so multiplier of a periodic point is the derivative of the function at the point z naught. Say I'll denote it by lambda. So take fp and take the derivative of the function fp at the point z naught and denote it by lambda. I'll say the lambda is lambda is the multiplier of the periodic point z naught. Now, depending on this value of lambda, so if we consider the modulus of lambda, so there are three possible cases. The first one is if mod lambda is strictly less than 1. If this holds, then I will say that my z naught is I'll say okay. So maybe is an attracting fixed point of fp. And similarly, second one is that if your mod lambda is equals to 1, so in this case, I will say that my z naught is this periodic point for f, or it is a fixed point of fp, it is indifferent. Just these are some just notations. Okay, so and the third one, if mod lambda is strictly greater than 1, then I will say that this z naught is repelling. And there are also two more classifications when mod lambda is equals to 1. So there are two cases. The first one is that if your lambda is equal to pi I alpha into z, okay, so not z, and your alpha is rational number, then I'll say this is rationally indifferent. And if this alpha is not in q, basically q complement, that is irrational number, then I'll say it is to be an irrational irrationally indifferent. Later, I will show how this classification is going to help us, and by this classification, we can actually find the dynamics of a function. So later I will see. Okay, now, yeah. So now, one more thing. So basin of infinity. What is basin of infinity? So this is basically set of points in C hat for which the points are going to infinity as n goes to infinity. So this set is also like important to know like what are the points which are going to infinity under the iteration function. So in particular, it becomes very much effective when we are trying to find out the dynamics of a polynomial. Okay. So let P be a polynomial of degree at least 2, because for degree 1 it has already been discussed in the first talk, so we are not interested in that thing. So we'll be talking about the degree which are greater or equal to 2. So if the degree of the polynomial is at least 2, then okay, yeah, so then maybe I should denote this set of basin of infinity by f infinity. Okay, now then f infinity, that is the set of points which are going to infinity under the iteration of a polynomial. This set, say this is basin of infinity, is completely invariant. So this actually holds. So maybe I should just illustrate this thing. Earlier I have given an example. So just simply, if you just look at this set, so here I have taken my polynomial to be z cube minus 1. Yeah. So now, not z cube, this is z square, I think. Z square. This is this is z square, z cube, what I wrote earlier. Z square, z cube, I think z cube it is. So no, z square, okay. Okay, now z square minus 1, then you can see what is the basin of infinity in this case. So in this case, the blue region, this blue region is basically the basin of infinity. If you take any point from here, it will go to infinity. And it is basically completely invariant. Means if you take any point from here, if you take the forward image or backward image, the point lies here only. It will not go inside this black region. And one more thing, that this is one. Second one is that infinity always lies in f infinity. So trivially, for a polynomial, we know if if my polynomial to be p, then p of infinity is infinity. So c, infinity is a fixed point of this polynomial. Then it is easy to check that infinity is always in the basin of infinity. This is trivial, right? Now, the thing is that in particular, infinity is us. Okay, so here I should mention one more thing. I have written here attracting if your mod lambda is less than 1. If your lambda is 0, in that case I will say it is to be a super attracting periodic point or super attracting fixed point of 8p. Okay, if lambda is 0, it is called super attracting. Okay, but if you take any polynomial, infinity is a super attracting fixed point of p, means p dash infinity is 0. So now the question is how to check the derivative of the polynomial at the point infinity. So it is an easy consequence to check this, that whenever I am talking about infinity and playing with infinity, so it is, and to check the derivative at infinity, it is enough to uh, take care of this function p of 1 by z and check whether g dash 0 equals to 0 or not. That means the point at infinity is transferred under this, it transferred to the point 0 for this function. So by checking this, we can say whether my g dash 0 is 0 or not. If it is 0, then I will say that it is a super attracting fixed point of the polynomial p. So it is indeed true that if you take any polynomial of degree at least 2, then infinity will be always super attracting. Means there will be some sort of area, or I can say domain, after which if you take any point, the points will be going to infinity. Okay. Now, I don't know whether I'm going in a like slow rate or not. Okay.
I think it's okay.
Huh?
It's fine. Yeah.
Okay. So means, yeah, almost 30 minutes. So I have to complete a lot of things. Okay. Maybe I'll write some facts on these are basically theorems. So before writing this theorem, I think I should write one more definition, which is field Julia set. So what it is? So field Julia set is basically denoted by Kp, and obviously it is for field Julia set stands for a polynomial. I will say you in a minute why it is not so important for transcendental function. So Kp is the set of points in C hat such that f in Z, this this sequence of functions is bounded. Okay, so this is called Kp. So in this figure, if you just look at, so what is Kp? So if you take any point, say Z here, and you keep iterating this, so this point will be inside this set only. If you take any point from here, it will come here, and once it come here, it remains here. If you take some point here, it will come first here, then comes here, and remains here. So that means the iterates of these points lie in a set which is bounded. So that is why I am saying this is important for polynomial, and if I take any transcendental function, so this actually doesn't hold, right? Okay, now, okay, so yeah, this is bounded, yeah, right. And why the term field Julia set? Why this term? Why this terminology? Why field Julia set? So I will just write in a minute that, as I have mentioned earlier, that the Julia set of this, maybe I zoom it to need to understand that the Julia set of this polynomial is basically the boundary of this, right? The boundary of this is precisely the Julia set of the polynomial. Last I mentioned. So this is the precisely Julia set. And the interior part of the Julia set, the interior part of the Julia set is basically filled. Filled with what? Filled with those points which are whose iterates are bounded. So this is a Julia set and whose interior is filled with those points which are in KP. So that is why I'm saying this is the terminology is like field Julia set. The interior of the Julia set is basically filled with points. Okay, now the theorems are that obviously, unless otherwise stated, we will always consider polynomial of degree at least 2. Okay. So the first one is that this Kp for a polynomial is a compact set. Second one, that the complement, if you take the complement of Kp, it is connected. And the third one, that the boundary of Kp is precisely the Julia set of P. So this is important to note, the third one, that the boundary of this set, the boundary of this Kp is precisely the Julia set of the function or the polynomial. Okay, so these are also some useful and standard results related to the polynomial. So, so the proofs are not very difficult. So that is why I'm just skipping it. Maybe if time permits, I can like revisit this proof. Okay, and okay, so now, okay, so I think it is clear that if you take any polynomial, so you will always have some finite region inside which you will find your Kp, and the complement of that set will be lying in the basin of infinity, right? So let me illustrate it by one more example. Maybe say you take anything like this one, no issue. Okay, so in this case, you
Sukant,
see, yes,
am I audible?
yes.
Yeah. I have a small question. So,
Yes,
since you have pointed out in a third point that boundary of KP is Julia's set of P, right? So,
yes.
so I'm asking, like, maybe it will you have not defined that thing, but I'm still asking. So that buried component can means like can they exist for this polynomial case?
Buried component. No.
Yes. No.
No. So no.
Okay.
No.
Okay.
So that is
Okay
a
then.
different thing, and that is more precise. So maybe okay, maybe I should define it
No,
here.
I'm just asking
So
for
what
this
Goran's point?
point.
Okay.
Yeah, that's fine.
Uh-huh.
Okay,
Uh-huh.
just I'm asking
Okay.
like
So as you have
since
mentioned, okay. So
just
as you have mentioned, let me tell you to the audience maybe what is buried. Buried means. So I wanted to skip this because this is a more complicated thing, not easy to understand. But it is easy for polynomials
yeah,
and
that
not
for
polynomial for
polynomial
rational
part.
maps. Yeah, for rational maps it is easy, but for transcendental setup it is not easy. That is why I wanted to skip this. Okay, buried means, okay, so as we have seen what is the Fatou and Julia set, and we first initially we saw that the Fatou set is an open set and Julia set is the complement of the Fatou set. And most of the cases we have seen the Julia set is nothing but the boundary of some Fatou set or some Fatou component, right? Julia set is precisely the boundary of some Fatou component. So, but it is not the case always. So there are some rational maps, and these maps was first given by Macmullen. There are some rational maps for which Julia points may not lie on the boundary of any Fatou components. So it is possible that there are some Julia points which are not lying on the boundary of any Fatou component. So that is the construction of these rational maps are something it needs some detailed idea. So I'm not going in that thing. Yes, for polynomials it is not true. So for polynomials it will be this kind of situation will not arrive. So buried means I'll say this is a point in the Julia set. So buried point means it is a points in the Julia set. Yeah. So buried, it's buried. The term buried stands for the points in the Julia set. Okay. Now, so we do not talk about points which are in the Fatou set and use the terminology buried. So this is for Julia set only, the buried. Okay. Now, okay. So maybe I'll go in a bit faster way because I thought I should cover a lot of things here, but the time is going so fast. So the first thing is that as I have, okay, let me define critical point. First, I defined periodic point. Now I am defining critical point. So what are the critical points? So if f is a rational function and the critical points are those okay, so let me write it in this way. Critical point are those where function fails to be injective, or in other words you can say where the derivative of the function vanishes. So those points are the critical points where the derivative vanishes or the f fails to be injective. Okay, so now for a rational map of degree at least 2, so number of critical points is at most 2d minus 2 in C hat. So I am considering in C hat. So infinity can be a critical point as I have seen for the polynomial case, and number of critical points is at most d minus 1 for a polynomial in C, not C hat. So if you take a polynomial of degree d, so here d denotes the degree of the polynomial. So then the number of critical points will be at most d minus 1. So these are little facts and not very difficult. So these are very easy. Now I'll move on to this thing that so see, depending on this critical point, as I mentioned earlier, depending on these critical points and periodic points, how the dynamics can be evolved for a polynomial. So I'll just write this thing. So this basically corresponds to the connectedness of the Julia set of a polynomial. So the first one is that if Kp means my field Julia set contains all the finite critical points, then both Kp and the boundary of Kp, basically the Julia set, these are connected. And if at least one of these critical points lie outside Kp, if at least one critical point lie outside Kp, then the Julia set and obviously and Julia set as well as my Kp, these are disconnected. In particular, these two sets have uncountably many connected components. Okay, so this statement can be visualized by this example. So see, for this function, so my Julia set was a Cantor set. See here, like scattered type of boundary is there for this polynomial, right? So in this case, my Julia set is disconnected as well as my field Julia set, which is also disconnected. Now, in particular, that example stands for a Cantor Julia set. Julia set was a Cantor. I mentioned earlier. Okay, now, so like these are little things which will help us to understand the dynamics in a more general setup. Let me define one more thing, okay, which is grand orbit. What is grand orbit? So grand orbit is basically the collection of points in C hat for which fnz equals to fmz for some mn in n. Okay, so or you can take it to be 0 also, n union 0. So what it is actually, so let me just illustrate this. Say I have taken a point z not here, and suppose I have taken a polynomial of degree 2. So that means if we pull back this point under P, I will have two preimages. Then if I pull back, I will have again two preimages, again two preimages, again two preimages, and so on. So this is basically the backward thing. Okay. Now when I move on to its forward thing, that is Z1. Now I will also consider what are the preimages of Z1. So one preimage was Z0, and the other preimage may be something, maybe Z minus 1. Now I will take its preimages. It will have two preimages, it will have two preimages, it will have two preimages, and so on. Similarly, I will take Z2 and do it for the same thing, take Z3, do it for the same thing like this. So I will take the set of all the points, like this backward thing, these Z1, Z2, Z3 things, these points, and these points. So all these points are basically lie in the grand orbit and no other point. Okay, now, so this is denoted by this third bracket of Z. So this set, basically the grand orbit of a point, this is the smallest. And as I have defined and illustrated this, you can always see that this is a completely invariant set, right? Because the forward images of these points are here, as well as backward images points are also here. So it is forward invariant. And one has to be careful that this set is not exactly equals to the forward images union backward images, because there are more points other than these two sets. So this set is the smallest completely invariant set containing Z. Now what happens if this set is finite? So means what happens if this Z is finite. So if there are such points for which the grand orbit is finite, we will call those points as exceptional points. So these are the collection of those Z in C hat such that this is finite. So these are called exceptional points. And I will just show in a minute that this set of points, basically the exceptional points for a rational map, can be at most 2. And also this holds true for the transcendental setup, that if for a transcendental map, exceptional points can be at most 2, not more than that. And okay, and this is equivalent. Yeah.
Actually, I have a doubt. Like, in some books, they have defined the exceptional point like this: set of all the backward orbit, collection of all the backward orbit, something.
I am
right
just
now you are.
I am
Okay,
just way to
so
write these things. I have written this in equivalent sign. What you are saying, I am just
okay.
way to write this.
Yes, yes.
Fine. Okay, so what you are mentioning, this is true, that this set, that the grand orbit is finite. This is equivalent to say that if your backward orbit is finite. So this is also, it can be shown that these two things are equivalent. Means it is enough to study the backward orbit, and if this is finite, then your grand orbit will be also finite. So it is enough to study. So that means what Koda is suggesting, that the exceptional points is the set of points such that this is finite, right, Gaurav?
Yes. So, okay, you are going to prove this equivalency, or can you suggest me some reference by which I can show?
Yeah, reference. These are this is there in the Bearden book. This is
Okay,
well written. Yeah.
Okay.
So one part is trivial, but the other part, for that I have to take an equivalence class and move on.
Okay,
so
fine.
this is
Yeah,
given
I will.
Bearden book. Yeah.
Yeah, I will go through.
Yeah.
It. Thanks.
Yes, definitely. Yes, yeah. Good. Okay, now what I have mentioned, that that set of exceptional points, it can contain at most 2 points. So I am going to prove this. So let me denote this set of exceptional points by E, capital E. So the cardinality of E is at most 2 for if rational. Yeah, but the proof will not follow for the transcendental setup, but although for the transcendental case also, we have this theory that the number of exceptional points is at most 2. Okay, so to do that, I'll just recall one thing which is called valency. It is well known to everyone, I think, that the valency of a rational function at a point, say we have, I'm writing my fz to be fz naught plus z minus z naught to the power k, ak plus dot dot dot, and say this k is the smallest, not ak, is k. K is the smallest natural number such that ak is non-zero. So if this is true, like we can always write a rational function in this form. So if you take this limit z goes to z naught, fz minus fz naught by z minus z naught to power k. Okay. So basically, if this limit exists and non-zero, then I will say that k is the valency of the function at z naught, or in other words, I can say that k is the local degree of f at z naught. Now, so this will help us to take to prove this. Okay, now So here one fact I'll just simply mention, this is called Riemann-Hurwitz relation, which says that for rational function, if you take sum of the points is sum of this expression. So this is denoted by d of say r z. If I consider that the point z naught, yeah. So the sum of this expression for all z in C hat is nothing but the 2 into degree of the map minus 2. So yeah, it needs to be proved. But yeah, I am taking this fact to prove this because it also takes some time to prove. Now say that under this expression, most of the terms will be 0. Because since I am talking about rational function, it has finitely many critical points. So this expression will be 0 because most of the points are basically non-critical because there are finitely many critical points. So, okay, so I am going to use this. Okay, now just note this. Now say, let the set E, that is the set of all exceptional points, say there are points which are more than 2, or maybe, yeah, you can take any finite number of points, k. Now, I'm saying that f from, and you consider f from E to E, and if for any ai not equal to aj, f of ai is not equal to, equal to f of aj, then we have something which is actually, let me denote it or in a picture, okay. So say this is a1 a2 ak, so this is a1 a2 ak, and if this happens, that suppose a1 is going to a1 and say a2 is also going to a1, so in this case we will have some contradiction. So the contradiction I am going to show in a minute, just let me know. So this cannot happen. That means for every ai not equal to aj, the images will never coincide. That means if acts as a permutation on E, that means there exists some natural number union 0 maybe, such that if n acts as an identity, right? Since we have a permutation map, then there are some iteration, then this permutation map will act as an identity map. That means my fn will be from E to E, and this is an identity map. So then what happens? If this is an identity map, then by this, okay, so in this case, let the degree of fn to be d. Now by the above Riemann-Hurwitz relation, what I have is that, now use the Riemann-Hurwitz formula for this function. Fn comma z minus 1, and I have taken that this is the degree of fn, that is 2d minus 2, and you can write this expression to be c in E C in C minus E, C hat minus E equals to 2D minus 2. And what is this expression? So this expression is nothing but, you see, what are the points E, what are the points in E? These are exceptional points. And what is the degree? Degree is D in this case, local degree. And how many points are there? I have taken k many points. So this is k into D minus 1 plus something. This expression stands for something, I don't know. So this is equal to 2D minus 2. So that means k into D minus 1 is less equal to 2D minus 2. And obviously you can see this cannot be a negative term, right? So that is why I am getting my k is less equal to 2. So that means I have taken this k. So I have shown that this is less equal to 2. That means it can contain at most 2 points. Yeah. So now I'll just end up this session by showing why this cannot happen. I have assumed this. Just I'll end up this session. Okay. So if suppose if one point is going to, suppose there are 2 points AI, AJ. Under F map, it is going to say AI. So then it means that AI has a pre-image which is different from AI, right? Right. So that means, so this is the pre-image AJ, which is different from AI. And similarly, if you take the pre-image of this, you can say that AJ has one pre-image which is different from AJ, and you keep on doing this. So that means ultimately you will get that AI has a backward orbit which is infinite, but it cannot happen because our AI is coming from the set E, for which my backward orbit is finite. So that is why this correspondence is not possible, and that is why F will act as a permutation map on this set E. Correct? So yeah, by this I think I should stop because it is the time is up. And yes, so maybe I just say in a few minutes, maybe 1 minute, that what I'm going to do in the next talk. Okay, maybe there are a lot of things, so I think I should stop here. Yeah, I should stop. Yeah, if you have any question, you can ask.
I think looks like there are no questions. So thank you, Sukanta, for your talk. So let's meet on next week then.
Yes, maybe Saturday same time, and yeah.
Yeah.
So I'll take this, and maybe I want to let you know that after this rational things, I want to move on to the transcendental setup. Maybe the third talk will be consisting the rational functions, and maybe on some day I'll move on to the transcendental functions.
Okay, that will be great. Okay.
Yeah. Okay.
Yeah. Thank you.
Okay.
Yeah.
Thanks. Thank you.
Yeah, thank you.
Okay.